What up, what up, what up, everybody? Alrighty, believe we're recording. Let's see what day we on. Day 16, let's go. Day 16, come on. For that money, I'm a fiend. I'm a goblin for the green. Alright, guys. I thought we should just turn up just a little bit. I'm lit. Let's go, guys. I'm feeling good today. I appreciate everybody for the support. Let me share my screen. Let's see. Yep, we on day 16. We're gonna do a little longer video today. Feeling good today, so hopefully we're gonna finish out all quick sort. Yeah, we're gonna finish all this right here, quick sort, and then we're gonna do the exponential time thing. I don't know why it didn't work when I clicked it. Yep, we're gonna finish all of this. This looks like it won't take that long. After this thing right here, I would like to go on GBT and ask it to make me like similar problems to, like, hey, give me a LeetCode style problem for insertion sort, right? Give me a problem similar to that, and give me a problem like merge sort and bubble sort, and then quick sort. So we can do 4 problems after that, just to like solidify my knowledge, you know what I mean? So yeah, so yeah, let's get to it. My bad about the sound in the back, because my AC is getting a little hot in here. But yeah, let's do it, man. We're at quick sort now. Yeah, so quick sort is an efficient sorting algorithm that's widely used in production and sorting implementations. Like merge sort, quick sort is a recursive divide and conquer algorithm. Divide. Select a pivot element that will preferably end up close. How long is this video? 4 minutes. Yep, we're gonna need to watch this video, because reading this sometimes it doesn't like click in my head, but it's all good. To center our sorted pack, move everything onto the greater than or less than side of the pivot. Oh, nice. Yeah, I get it. So what happens is, select the pivot element that will preferably end up close to the center of the sorted pack. So let's just say 1 to 10. Obviously it'll be 5. And then you're gonna move everything onto the greater than or the less than side of the pivot. The pivot is now in its final position. Recursively repeat the operation on both sides of the pivot. So it's gonna do another pivot from 1 to 4, which is 2, and then another. Damn, bro, what the hell is that? Am I tripping? Or the array is sorted after all elements has been through the pivot operation. Explainer video. Right,
quick sort is fast and efficient, and unlike some of
I ain't gonna lie, man, that shit loud as hell for me, man. Hold up. All right.
the other algorithms that we've covered on this channel, it's actually used in the real world. Looking at you, Bubble Sort. Quicksort is a divide. Quicksort is fast and efficient, and unlike some of the other algorithms that we've covered on this channel, it's actually used in the real world. Looking at you, Bubble Sort. Quicksort is a divide and conquer algorithm, just like merge sort. And while it technically has the same big O complexity as merge sort, order n log n, it doesn't require so much memory, and it doesn't have to copy elements from sublist to sublist. It actually sorts the entire list in place, which means that it can be more performant. All right, let's dive into how it works. We'll start with a random list of numbers. The first thing we need for quicksort is a pivot number, and to keep things simple, we'll just arbitrarily use the element at the end of the list. In this case, 5. Next, we need 2 pointers, I and j, to keep track of things as we're gonna be swapping them around. I will start at index -1, which of course isn't a real index, but we need to be able to increment into index 0 on the first swap. Then j will start at index 0, which is 8. So in this case, we'll be comparing 8 and 5. And because 8 is not less than 5, meaning j is not less than the pivot, we don't move.
Hello. Damn, bro, my headphones are tripping, man. Sorry,
into index 0 on the first swap. Then j will start at index 0, which is 8. So in this case, we'll be comparing 8 and 5. And because 8 is not less than 5, meaning j is not less than the pivot, we don't move I, but we do increment j. Now we do it again. We compare j to the pivot, 3 to 5, and because this time j is less than the pivot, We increment I, then we swap I and j. Now I understand that it's a bit funky. We are comparing j and the pivot, but actually swapping I and j. Just remember that. All right, and now we just do it again. So now we'll compare j to the pivot again, in this case 2 and 5. And again, because j is less than the pivot, we increment I, and then we swap I and j. Next, we compare 9 and 5. Now this time j is greater than the pivot, so no swaps. We move j forward, but we do not move I forward. 1 is less than 5, so we move I up, and we swap I and j. 7 is greater than 5, so no swaps here. 6 is also greater than 5, again, no swaps. 10 is greater than 5, no swapping. 4 is less than 5, one last swap. All of the numbers at or to the left of I are smaller than the pivot, and all of the numbers to the right of I are greater than the pivot. If we swap I plus 1 with the pivot now, then the pivot will be in its perfectly sorted place. Now, that's just one round of the partition function in Quicksort, but frankly, it's the interesting part. The way we turn this partition function into a full-blown Quicksort is by recursively calling this partition function. So we'll continuously partition, do this algorithm, over and over on each half of the list until the full list is sorted. Now, remember how I mentioned that Quicksort is generally more performant than merge sort? That's true, but it does have a dark side. If we consistently pick the smallest or largest element from the list as the pivot, it gets really slow and will actually degenerate into order n squared in Big O terms, which effectively makes it a bubble sort equivalent, which is something that no sorting algorithm wants to be. But honestly, that shouldn't scare you. There's pretty trivial ways to make sure that Quicksort never degrades. For example, we can just check and make sure that the list isn't pre-sorted. We could randomize the list before sorting it, or we could even pick the pivot at random for maximum chaos. Anyways, optimized versions of Quicksort are used all over the place in the real world. Most languages' standard libraries actually do use Quicksort, at least for part of the standard implementation of their sorting algorithms. Now, so you can properly visualize it end to end, here's a full animation of Quicksort on a larger data set. And here's another full animation, but where the list is already sorted and the performance degrades. You'll notice that it's a lot slower.
Damn. I feel like I get it and don't get it. It's kind of like... Okay, pseudocode. Select the pivot element. Will arbitrarily choose the last element of the list. Move through all the elements in the list and swap them around until all the numbers less than pivot are on the left and the numbers greater than the pivot are on the right. Move the pivot between the two sections where it belongs. Recursively repeat for both sections. Assignment. We are now have two sorting algorithms. Quicksort. Okay. Fucking is it been 1918 about COVID? Quicksort is fast on large data sets. Quicksort is fast on large data sets like merge sort. Okay. But it's also lighter on memory usage. Let's use the Quicksort for both follower count and influencer revenue sorting. Complete the Quicksort and partition functions according to the given algorithms. The process is to start. It started with Quicksort A. The process started with Quicksort A 0 and then A minus 1. So nums is A? I'm confused. Okay. Quicksort. So nums low high. If Quicksort. If low let's understand this. If low is less than high, if low is less than high, if low is less than high, partition the input list using the partition function stored with the returned middle index. Bro, we already started off with this shit. Partition the input. Okay. I feel like I don't like. What do I need? For quicksort, the base case is simple. Only continue if the section you're working on has more than one element. The core of this is to divide and conquer. You're breaking the list into parts around a pivot. After you partition, you'll get back the pivot index. Everything left of it is smaller. Everything right. Confusing I and J position. Remember, I trails behind, marking where the small values end. Okay. Choose the pivot. Okay, to start with quicksort function, this is what I am thinking. So what I'm thinking is, one, the first step. So if low high, quicksort high should be like the highest number, low is the lowest number. Okay, wait, we gotta understand. I think this right here is what's making sure like the pivot, like pivoting stuff, right? So yeah, we set pivot to the index high, set I to the index low. But let's start with this first. I understand this, it's just this one. So if low is less than high, so if low is less than high, partition the input using the partition function and store the middle index. Recursively call quicksort on the left, on the right side of partition. Recursive means when you call itself. Partition the input list using the partition function and store the returned middle index. The middle index is just the end one. So if I do one, if low less than high, right? 2. Now Partition the input list using the partition function and store the return middle index. I'm confused about this. I am confused about reports below. Establish a logic for lines 2 to 4. Partition the input list. You're calling partition nums function here. This function rearranges the list so that all items less than the pivot are to the left. All items greater than or equal to the pivot are to the right. It will return the pivot's final index. Let's call it pivot index or min.
Quicksort is fast and just arbitrarily use the entire list in place, which means that it can be more performant. All right, let's dive into how it works. We'll start with a random list of numbers. The first thing we need for quicksort is a pivot number, and to keep things simple, we'll just arbitrarily use the element at the end of the list. In this case, 5. Next, we need 2 pointers, I and j, to keep track of things as we're going to be swapping them around. I will start at index -1, which of course isn't a real index, but we need to be able to increment into index 0 on the first swap. Then j will start at index 0, which is round. I will start at index -1.
I will start at negative index 1.
Which of course isn't a real index, but we need to be able to increment into index 0 on the first swap. Then j will start at index 0, which is 8. So in this case, we'll be comparing 8 and 5. And because 8 is not less than 5, meaning j is not less than the pivot, we don't move I, but we do increment j. Now we do it again. We compare j to the pivot, 3 to 5, and because this time j is less than the pivot, we increment I, then we swap I and j. Now
We increment I, then we swap.
Understand that it's a bit funky. We're comparing j and the pivot, but actually swapping I and j.
We're comparing j to the pivot, but we're swapping I and j.
Just remember that.
We're comparing, so exactly, okay.
All right, and now.
So we're comparing, so the way it works is that I starts at -1 index, and the way, okay, -1 index, and then -1 index, and then we're comparing j to the pivot. If j, sorry, if j is less than the pivot, we're gonna swap the index with j.
Now we just do it again. So now we'll compare j to the pivot again, in this case 2 and 5. And again, because j is less than the pivot, we increment I, and then we swap I and j.
No, we swap I, since j is less than the pivot, we increment j, and we increment I, but we switch.
Next, we compare 9 and 5. Now this time j is greater than the pivot, so no swaps. We move j forward, but we do not move I forward.
Yeah.
1 is less than 5, so we move I up, and we swap I and j.
We move I up, and then we swap I and
7
j.
is greater than 5, so
7 is greater, so we increment j and don't move I.
No swaps here. 6 is
6 we leave
also
it.
greater than 5, again, no swaps.
10
is
as
greater
well.
than 5, no swapping. 4 is
4 is less than the pivot, so we switch 4 with I.
less than 5, 1 last.
Oh, so that we first increment I, then you switch. Okay, you don't move the current. You increment first, and then you switch.
All of the numbers at or to the left of I are smaller than the pivot, and all of the numbers to the right of I are greater than the pivot. If we swap I plus 1 with the pivot now,
if we swap I, so then now that finishes. Now, once the whole process is done, we switch I plus 1 with the pivot.
Then the pivot will be in its perfectly sorted place. Now, that's just one round of the partition function in Quicksort, but frankly, it's the interesting part. The way we turn this partition function into a full-blown Quicksort is by recursively calling this partition function. So we'll continuously partition.
Recursive meaning in programming Python.
What happens when a function calls itself in Python? You'll see here inside the function factorial, we're calling factorial. This is called recursion. If we want to take the factorial of n, it's just n times n minus 1 all the way down to 1, which is considered the base case. But until we satisfy this base case, we have to keep multiplying n times n minus 1. But what happens when a function calls itself in Python? You'll see here inside the function factorial, we're calling factorial. This is called recursion. If we want to take the factorial of n, it's just n times n minus 1 all the way down to 1, which is considered the base case. But until we satisfy this base case, we have to keep multiplying n times n minus 1. But what happens when a...
Oh, uploaded already?
Oh. What happens when a function...
Hold up. If n is less than 1, return 1, else return n times let's trace through what happens when we call factorial 5. Factorial 5 is 5 times factorial 4. Close this off. And minus 1 by itself just calculates the value and doesn't do anything with it. It's like writing 5 minus 1 or paper. You get 4, but nothing happens with the 4. The function never changes n. So say that with 3, then you go back, then 3 goes to 2. I get it. I see. My bad, man. I was trying to understand what this recursive shit means. It's like confusing me a little bit. We now have 2 sort algorithms. So I see how quicksort works. The process started with quicksort. If low Quicksort, think of this as the brain. What it does, it divides the array into 2 parts, left and right of the pivot, and recursively sorts them. How it works, checks if low is less than high, right? This just makes sure we're not sorting at a 1 element list or something invalid. Partition you call. Okay, so if low is less than high, we're gonna do the partition. We're gonna call partition. Partition the input list using the partition function. To partition the input list using the partition function and store the return middle index. So partition low, high. Now recursively call quicksort on the left side of partition. So quicksort on the left side of partition is gonna be len of nums quicksort this is the right side. See what GPT says. Okay, you're not storing the pivot index. Right, we're not. We call partition, but you're not saving its return value. Remember, partition gives you the pivot's final index. You need this to know where the split of the list goes. Store the result of partition. So the Pivot. That's what it wants. It wants to partition. Pivot. If index is equal to partition. Bro. Oh, I don't get this, so I'm gonna need help on this. Like how to do this, cause I can do this on my own. Like, but it's like giving me steps to do it. I don't fucking like that. But you're not saving its return value. Cool. Store the result of partition in a variable like pivot index. Your recursive calls are slicing. Yeah, that's wrong. Store the result of partition low in a variable called pivot index. Right. Call quicksort nums low pivot index -1. Call quicksort nums pivot index. I don't get this shit, bro. I get the video though, like the pivot index. We want to store that. That's all the way to the right. So what is it saying? Partition of this is hard as fuck, bro. I don't get this shit. At the end, I'm gonna just have to understand this because I don't fucking know what the fuck is going on, bro. Right now you're assigning the function itself to pivot index, not the result. You need to call the function and pass the parameters. Right? You're calling the functions. How it works, big picture. Pick a pivot. We'll use the last element of the list. Rearrange the list so everything less than the pivot goes to the left. I know how it works. I meant this. No, I meant this. I understand how quick sort works, not what the code is doing. So if low high, this is the base case for recursion. You're saying only run the code below if there's more than one element to sort. Otherwise, the function just returns nothing to do. Pivot index partition lums low high. Oh, so then pivot index. I see. So what this does is pivot index is getting the nums, is getting the left side so low. Pivot index. So right side of partition. So if okay, pivot index nums high. This calls a partition function which pivot typically nums high, right? Rearranges the list. This calls the partition function which picks a pivot, typically nums high, right? Rearranges the list so that all elements less than the pivot is to the left. So fix the pivot. Returns the index with the pivot. This line recursively sorts the left side of the list, everything before the pivot. Recursively sorts the right side of the list, everything after the pivot. It never said divide left side, right side. It just said that, like, pivot right here. That's why I'm confused. Like, they're not even dividing it in half. I don't know. Alright, let's try this one. So set pivot to the element at index high. So pivot is equal to the index high. So the index high, we don't want the element, we want the index. So if I put high, it's just that's wrong. Okay, fuck it, we'll put high. Then we do set I to index below low. I is equal to low minus 1. Now for each index j, so for j in range low to high, I did what I was doing. If the index if j is less than the pivot, Right? If j is less than the pivot, we want to increment I, so I plus equals 1, and then if it's low, then you switch I with j. Swap index I with j. Boom, got it. So j is equal to j I. Swap the element of the right. Swap the element. Swap the element of the right of I with the pivot element. So we want to swap I with I plus 1 with pivot to pivot I plus I plus 1. I feel like I'm doing something wrong. I should be calling like nums before something. Return the new index of the pivot element, the item in the middle of the return the new index. New index. You're setting pivot high, which is fine if you're referring to the index. But later you're comparing j is less than pivot, which means you're comparing the index j with the index pivot, not the pivotal value. So then this has to be nums. And then j here gotta be nums. Holy shit, it does that again. Right? Okay, I get that. Now, if j is less than pivot, right now you're checking if the index j is less than the index pivot. Yeah. If what the fuck? I got that. That should be right. The line should swap indices, but it should swap elements of the list. You need to swap the elements of index I and j and nums. So what the fuck would it be, like nums? Don't ever do that again. Ah! Okay. Alright, hold up guys, I'm getting a call real quick. Alright, sorry guys. I guess, wait, how is that not doing anything? It should be switching it. Oh my god, it should be equal. That's on me. You're returning I. At the end of the partition, you're returning I, but you should be returning the pivotal's final index. I plus 1? Oh, yeah, it is. Because that gets it before. This should work. Fail. Darn. I think it's the equal right here. I don't know why I did that right there. Something's an issue here. You're swapping the pivotal value, not the actual element. Wait, the value. You're swapping the pivotal value, not the actual element in the list at high. You need to swap. How do I choose this one? So, right. What am I doing? I'm swapping the next element when num's high. Oh shit. Ah damn, that's on me. That is on me. I understand. Damn. This one was a doozy, I'm not gonna lie. I didn't like this one. Okay. I would like you to explain bit by bit everything that is going on. So I understand everything about... What's this, quicksort? I think this is quicksort. Okay, let's see if I understand it first. So what's happening here is we're calling quicksort, and if low, so this checks if there's even how do I explain it? If there's even, because if it's less than 1, then you can't do anything really. It returned nothing. Then the pivotal index, what this is doing is getting the partition where this is where the recursive shit is happening. So it's getting all this and then quicksort. So this is returning. Okay, I'm kind of confused about this shit right here. I'm gonna be honest with you. So what's happening here is pivot is equal to num's high. So is getting the pivot is the last element. Not the index, just the last element on the nums, which is high, and then I is low minus 1. So it's the lowest one. Remember, it's like I, but before, and then so if J in range low to high, yeah, we want the index. We didn't want the value. If they wanted the value, I would have put len here. So we get the index of J from the beginning, and we're checking if the nums J is less than the pivot. We're gonna increment I, and then we're gonna swap I with J. Okay, I get this part perfect. I don't get this shit, honestly. So you're implementing quicksort, a divide and conquer sort element. It works by picking a pivot, which is the last one, putting that pivot in its correct spot. Okay, putting a smaller values to the left, larger to the right, recursively sorting both sides. Okay, quicksort nums low high. the main function. Python, this is a recursive function that sorts the sublist nums low, high, plus 1. Python if base case. Only sort if the current sublist has more than one element. So if low is greater than or equal to high, we stop because so if low is greater or equal to high. I never done that. If low is greater than or equal to high. Which is less than high. If low is greater than high, we stop because I don't think this is right. Pivot index. So this one, okay. What this does, this calls the helper function partition to choose a pivot, right? To choose a pivot, rearrange the list so that all smaller values go to the left of the pivot, all larger values go to the right of the pivot. Then we return the index of the pivot after it's placed in the correct position. So quicksort nums low pivot -1. Now recursively sort the left half of the list, element smaller than the pivot. So quicksort nums pivot index +1 is high. So okay, based off of what this says is, so what this does is just literally everything we worked on right here, we're putting into a variable called pivot index, which what this does is what was it explaining? So what this does is all it does is it returns the index of the pivot, which is the last one after it's placed in the correct position. Now recursively sort the left side of this. Okay, so then quicksort. So what we do, recursively sort the right half of the element. So pivot index +1. We want to go to the next, to the right side of the list, elements larger than the pivot. So partition, the helper function, Python. Okay, anyways, pivot nums high. Wait. Okay, I understand how this one works. Yes, please do that, whatever this means. Let's see it actually running. So nums 83159. So quicksort the nums 0 4. 1 2 3 0. Low is 0. Low is 0, high 4. So nums 4 would be 0 1 2 3 4. Why did I do 1 through 2? Yeah, okay. We're counting 0. As low as 0. Oh, these are the indexes. Okay. Okay. Indexes. So the pivot, what the pivot's doing is, alright, so the pivot is nums high, so that's the last number in the list, and I is where we increment. But hold up. So first call quicksort nums 0 4. Okay. So call partition nums 0 4. Pivot is equal to 9. I is equal to -1. Right. So loop through j equals 0 to 3. So j is 0, nums is j is 3, which is the second one. And then we'll do, because I is -1, so it's not on here yet. So what we're doing is 0 to 8. So 8 is less than 9. So we're swapping I. So 8 is less than 9. So I 0, swap 0 with nums. That does basically nothing. Then we're doing 1, j is 1. So we incremented I now, so that should be 1. Yep. So we do 3. 3 is less than 9. So now we're switching 8 with 3. Why is it not showing that? Yeah, this one's showing. That one didn't. That's weird as fuck. Second call. Let's do this one. So the pivot nums 3 should be 5. Oh, he's doing the calls. So recursive calls 0, 3, and it does it again. 3. Then it's gonna do. Now we're switching 8 with 1. 5. 7, 8, 9, high. I think I get it. Damn. It's kind of tricky. Quicksort big O. On average, Quicksort has a big O of O and log n. In the worst case, and assuming we don't take any steps to protect ourselves, it can degrade to O n squared. Partition has a single for loop that ranges from lowest index to highest index. Partition has a single for loop that ranges from the lowest index to highest index in an array by itself. The partition function is O(n). The overall complexity of quicksort is dependent on how many times partition is called. Worst case, the input is already sorted. An already sorted array results in a pivot being largest to smallest elements of each time, meaning partition is called O. So it's doing from low. Yeah, it's from. Okay, it's called is n times. So best case, the pivot in the middle of the element of the sublist, which results. Okay. What causes quicksort to break down to O(n squared? An unusual large list, an already sorted list, a small list, a randomized list. It's already in an already sorted list. That would be messed up. What is quicksort's worst case? Big O(n squared. What does shuffling quicksort's input do? Slows down the algorithm. Practically ensures that in time. Makes algorithm unsafe for production. Makes it really slow. Yeah, I don't know what the other ones meant, but why is the median of 3 approach sometimes used? Why is the median of 3 approach sometimes used? Median of 3. Oh, okay, let's read this, because what was the last one? Like that? Fixing quicksort. Oh, yeah, it was. Well, anyways, while the version of quicksort that we implemented is almost always able to perform at speeds of O(n) or log n, 8 times log n, its big O is still technically O(n squared due to the worst case scenario. We can fix this by altering the algorithm slightly. 2 of the approaches are shuffle input randomly before sorting. This can trivially be done in O(n) time. Accurately find the median of a sample of data from the partition. This can be done with O(1). Random approach. The random approach is easier to code, which is nice if you're the one that writing the code. The function simply shuffles the list into random order before sorting it, which is O(n) operation. The likelihood of shuffling a large list into sort order is so low that not worth considering. Median approach. Another popular solution is the median of 3 approach. 3 elements, for example, the first, middle, and last elements of each partition are chosen and the median is found between them. That item is then used as the pivot. This approach is less overhead and also doesn't require randomness to be injected into the function, meaning it can remain deterministic and pure. Why is the random approach sometimes used to use less space to make the algorithm harder to understand? It doesn't require randomness and purity. Maybe this one. Why use quicksort? Pros: very fast, at least it is in average case. In place, saves in memory, doesn't need to do a lot of copying and allocating. Cons: typically unstable, changes the relative order of elements with equal keys. Recursive can incur a performance penalty in some implementations. Pivot sensitivity: if the pivot is poorly chosen, it can lead to poor performance. If you need a stable sorting algorithm, which one would you use? stable sorting algorithm. All of them has cons in it though. All of the quizzes used in real world because the trade-offs are often worth it. For example, in default in PostgreSQL, a popular open source database. I'd also like to shout out TimeSort, a hybrid merge sort and insertion sort that was used by Python's default. See, look, there's always cons to stuff. So like, this question is a doozy. If you need a stable sorting algorithm, which I know what, I'm curious. Let's see what Google has to say. Merge sort or insertion sort are good choices. Is Quicksort one? No, Quicksort not still other than preserve. Yeah, it has a lot of cons. Merge sort. Merge sort is when. Yeah, so merge sort. What this does is first half, second half, then implement. Yeah, I remember this one. Kind of like this one as well. I don't know. What we got here? Just questions, and then we have one last one. Why use Quicksort? Okay. Which would you most likely use in a large production system? Obviously Quicksort. Holy shit, that lag was insane. Bubblesort is shit. Bubblesort is like, hold up. Bubblesort is when swapping is true and like, so while swapping is true for iron range, if nums next to it.
Bubble sort is the sorting algorithm. Otherwise, we just leave them be.
Yeah, it's the one you see next to it. Anyways. Selection sort. How many sorts are there? God damn. Selection sort. Another sorting algorithm we never covered in depth is called selection sort. It's similar to bubble sort in that it works by repeatedly swapping items in a list. However, it's slightly more efficient than bubble sort because only makes one swap per iteration. However, it's more efficient than bubble sort because it only makes one swap. Yeah, one swap per iteration is bubble sort. Selection for each index. Okay, so we're doing the index, not the value. So for index in range 0 to nums. We're doing len. Does that make sense? Index. So 0 to 8. Right, cool. But what if I put nums? This would cause an error, right? I caught that on really fast. Yeah, boom, bet. Come on, I'm understanding this a little bit faster now. Set the smallest index to the current index. So smallest index is equal to the index, right? So another for loop. Holy shit. For each index from small, so for small index and so for small index, I don't like how I said that. For I and for each index is smallest index. For each index from smallest index plus 1 to the end of the index. So for same shit range. So smallest index plus 1 to to the land of nums. Right? I did not mean to do that. If number at this inner index is smaller than the number of the smallest index, is smaller than the inner index. Okay, so if the number at the inner index so if nums index is less than, if the number of the inner index is smaller than the number of the, wouldn't it be the other way around? I think it's the other way around. I'm pretty sure. No, we're doing I. If nums I is less than, see, that's the one in the next one. We're doing the next one, right? That makes sense in my head. I don't know if I'm wrong. Set the smaller index. Wait, what? If the number in the inner index is smaller, what the fuck? Too many indexes. If the number at the inner index is smaller than the number at the smallest index, set the smallest index to the inner index. So inner would be, so if we're doing nums, if we're running, it's gonna give me error. Oh my god, just do pass. If the inner index, this has to be the inner. If the inner index is smaller, bro, that makes no fucking sense. This has to be the big. Bro, I'm doing how I did it, bro. If the number in the inner index is smaller, I don't understand what means inner, bro. I'm gonna crash out. So yeah, that's wrong. Okay, so I guess we're doing the inner index, which is index. So we're doing nums index is less than nums, which is that one. Right. Set the smallest. Set the smallest. The smallest index is equal to the inner index, which is num. That kind of makes. Oh, we're comparing the wrong way. What the fuck? There should always be the num's smallest index. So num's I, that was right before. So num's I is the we can't call that. That's why we can. Oh, I get it. I see. I think I get why. But if the smallest index so if num's I is less than num's what's that? I want to set the smallest index to equal to I, and then swap them. Yeah, I got it. So now I need to swap them. Okay. Swap the number at the current index. So now I need to set that to that. Okay, it has to be something right here. And then we gotta return. We have to return nums. Now I just gotta figure out how to swap. So I gotta swap. So let's understand the logic. If say 10, 9, so the smallest index is index, which is the first index. So the first index. So now we're doing this. Now we're doing another for loop. If num's I is less than, we want to make the smallest index to I. Now swap the number at the current index. So we're gonna swap. So nums index. No. So smallest index. I don't know how to swap this. So nums index, smallest index is equal to smallest in. So do I put nums in front of it? Smallest index times nums. It's not getting the 3, 5. Not getting the. So I don't know. So what was it? Oh shit. Let's fucking go. I got this right. I'm so lit. Oh my god, I got that right. I always mess up on that. Every flipping problem, bro. Let's go. I got it. I get it. Let's go, boys. Yeah, I should have put I and J. I need to start doing that. Let's go. Alright, we can let's finish this out. Exponential time, and then tomorrow we're going into the deep waters. Let's do it. So polynomial versus exponential. Broadly speaking, algorithms can be classified into two categories: polynomial time and exponential time. Polynomial time, O of 1, O of n. Okay. Exponentials, O of 2 part of n, right? Technically, O n factorial is factorial time, but let's lump them together for simplicity. An algorithm runs in polynomial time if its runtime does not grow faster than n to the power of k, where k is any constant of n. Okay. To put it simply, polynomial time algorithms can be useful, but exponential time algorithms are always too slow to be practical unless you're trying to force them to be slow. N is as low as 20. Right. So polynomial algorithms are blank than exponential algorithms. Faster. Polynomial time equals p. So back in the 1970s, some computer scientists wanted to come up with good descriptive names for set of polynomial time algorithms. After much deliberation, they settled on the letter P. Naming things is hard. The hand-wavy takeaway is that problems that fall into class P are practical to solve on computers. Problems that fall into class P are practical to solve on computers. Problems that don't fall into P are okay. Algorithms in P are blank than algorithms not in P. More practical algorithms. More practical. It's not easier to write, but it's more practical. Oh shit, we gotta. Oh no. No. Alright. Oh lord. Okay. Reduction to P. Let's take an exponential time algorithm and fix it up so it can run in the polynomial time. The Fibonacci sequence is a sequence of numbers where each number is the sum of the two numbers for it, like 0, 1, 0 is 1, 1, 1. Wait, Fibonacci. Fib 0 is 0, Fib 1 is 1, Fib 2 is 1, Fib 3 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 8 plus 5 is 13. Here are implementations details to do it in a polynomial. The input n represents the index of the desired Fibonacci number. What? The input n represents the index of the desired Fibonacci number. What the hell does that mean? Represents the index. Okay. So for I in range 0 to the len of n. Did I put more? Yes. Right, we want the index. Initialize the three variables. So GP is equal to 0. P is equal to 1. And a placeholder, the current, store the new Fibonacci number at. So current. So the current is equal to a placeholder current to store the new Fibonacci number at each step. Write a loop that iterates n minus 1 time. For example, if n is equal to 2, 1 iteration occurs. What? Write a loop that iterates. So for iter and range. So for iter and range, why don't that erase n minus 1 time? For example, if n equals 2, for iterate, write a loop that iterates n minus 1 times. For example, n equals 2, n equals 2, 1 iteration. If n equals 2, 1 iteration occurs, right? Oh, okay. You know what I realized is that I think I need this. I just this is not gonna work. I don't think this is gonna work. No, my video. Yeah. Oh, sorry guys. Where were we at? So return current. I don't think this is gonna work. What? Where the fuck around this part? It has no line. Shit. It's not gonna work. But so I think this is what it's doing. Is the input is 10, 17, expecting 55. Same thing here. Don't tell me the answer. Your variables are up with updates on here. Incorrect. think of how you slide the window Fibonacci. The new GP should be the old P. The new P should become the current. So GP should equal P, and then right, and then this will equal GP. So your loop range is fine, I might as well, but make sure the starting return values are correct for small n. So you might return the wrong value. You want to handle the first two case. Hold up, bro. Whoa, I mean that. The problem is this line. You're setting P. You're setting P to the new GP. But oh my god, I meant current. I meant current. Alright, my bad guys. Okay. This passed, but this is an issue. I think he's not getting the first one. Damn, okay. So if n is equal to 0 or n is equal to 1, return let your loop handle the n. So it's gonna check. So return n. Let's fucking go. Yeah! Let's go, man. Okay, I'm gonna do all these rest of these on my own. I promise you tomorrow when you guys come back. Yeah, I'll do all this on my own. I just gotta go eat right now. So I appreciate you guys for watching. Yeah, I learned a lot today. I'm getting better every day, so yeah, hopefully you guys are learning with me. But yeah, so this was day 15 or 16. Let me check real quick. Google. Oh shite, I clicked the wrong thing. This is day 16, so yeah, appreciate you guys for watching this video, and give a like and subscribe. So yeah, and join the Discord on my bio. See you guys.